Okay, well, thank you very much for the organizers to invite me to lecture here. I will spare you my handwriting on a whiteboard or on a blackboard because it's apparently very difficult to read. So I will write on the iPad, which today means I will have to sit down. And so apologies for not standing up and lecturing to you in this way. Anyway, so the motivation for giving a talk, maybe let me just start sort of giving a little bit of motivating ideas. So why would you, or what is, first of all, geometric engineering? So it goes back to the early 90s, and it essentially started off being a way of constructing gauge theories using geometric tools in string theory. So you have some string theory or M theory, and then you try to engineer a gauge theory using sort of tools that you have in geometry. So why would you want to ever do such a thing? Well, so motivation. Well, the first one is when at CERN, as a particle theoretical or whatever physicist, well, we would like to perhaps engineer the standard model. So when at CERN, we should certainly ask ourselves, can we geometrically engineer the standard model? And at this point, I will, I think for the first time at the school, which is quite, something, given that we already had so many lectures, use the elephant in the room, namely the word supersymmetry, that we actually will have sort of supersymmetry in the back of our minds. Whenever we do this, our tools basically require us to have some supersymmetry in the field theories that we engineer. So actually, what we'll be doing is, there's lots of seats back here, there. So we'll actually be looking at, say, a four-dimensional n equals 1, supersymmetric gauge theory with the standard model gauge group as U3 as U2 times U1 plus matter plus U-Carver couplings. And that, of course, for many people will be such a retro thing to do, given that supersymmetry doesn't seem to be materializing, that you might ask, so why am I at this lecture? Isn't this something that you should have taught 5 years ago, which I actually did at that time? So I actually brought this picture because it's my favorite picture of CERN of all times. This is just out there in 2012 at 4:30. I checked the time on the 4th of July. Everyone was super excited. The Higgs is going to be discovered. Everyone waiting to get into the lecture room. And so we would like to have seen something like this for supersymmetric theories. That's not happening. So at least as far as I know, but we might want to go to the lecture theatre over there and ask these people what they're talking about. Anyway, if in doubt, you might say, can you bring up some other motivations? So one other sort of very important motivation is, well, we can look at particular theories, namely supersymmetric and conformal theories. So SCFTs. And can we geometrically engineer these? And in fact, at the very beginning, this was already sort of motivation for four-dimensional n equals 2 theories. But more recently, as you probably have heard, a lot of these theories have been, so there's been a lot of progress making use of geometric engineering to actually get a hold of supersymmetric conformal theories. So let's just recap. In dimension less than or equal to 6, there are such theories. They exist in those theories. And for maximal supersymmetry, we understand these very well. So this is like, for example, the 6D2,0 theory, or n equals 4 super Young nulls in 4 dimensions. And essentially, there we know almost everything about how they're classified. We don't understand them, of course, in their full glory, but we kind of know a lot about what type of theories they are. And basically, the only characteristic that you have there is a gauge group, which is classified in terms of A, D, or E. For less than maximal supersymmetry, the situation is quite different. So in 6 dimensions, you can ask, what are the superconformal field theories in 6 dimensions with one supersymmetry? So n equals 1, meaning you have a chiral supersymmetry, it's sort of half the supersymmetry from the maximally supersymmetric case where everything is just a gauge group ADE. And actually recently, this was achieved. So classification achieved using geometric engineering. Yeah, so basically in what is called F-theory. And for those of you who don't know what F-theory is, don't be scared. I will not really explain it because I actually won't be talking about F-theory, but what you should think of is it's type to be a string theory where you have the axial dilaton varying. It undergoes SL2Z self-duality monodromies, and the loci where that happens, they are so-called 7 branes, and they are sort of generalizations of your standard D7 branes. Okay. So you can do this sort of geometric engineering of superconformal field theory, or just gauge theories in general, in sort of various ways. One is you write down a string theory. So one approach is, essentially 2 approaches, but yes, one approach. You start with string theory or M theory in 10 or 11 dimensions, and you find some compactification space that gives you an RD minus 1, 1 comma D minus 1 times a compact space MD. And then asking the properties of this compact space MD to actually reflect the properties of what you actually get in the transverse Minkowski space. So the geometry and the topology of MD determine the Lorentz effective theory in R1 comma D minus 1. So this is approach say A, and there's another approach with approach B, where you say, well, let's, we're looking at gauge theories, so let's just consider branes in such scenarios. So this is sort of branes probing such geometries, such compactifications. And it's usually very essential to find ways of seeing when exactly does a certain geometric property result in a feature in the gauge theory when I probe it with branes or if I compactify it to lower dimensions. Okay, so let me actually give you an example, and this is sort of the example that really will come up all the time, so I would like to sort of spend a little bit of time doing this, and it's a well-known example, which is named the 6-dimensional 2,0 theory with some gauge group G equals to ADE. Right, so we said there are 2 approaches. One is compactify and get this theory. The other one is take some branes, probe, and get this theory. So of course, the second approach, the B, you get by looking at M5 branes. At least the A time, right? So for A time. So you take a stack of N and 5 branes, and then the effective theory is this theory, putatively. So for a single M5 brane, we know exactly what that theory is. Okay, so for n equals to 1, so we're saying this is G equals U1, and then basically this is what's called it's the 2, 0 tensor multiplet. And so essentially in 6 dimensions, we have our Lorentz group SO1, 5 times an SO5R symmetry group for the maximum supersymmetric theory, and they fit inside the OSP 6,2/4 superconformal algebra or group. And the abelian tensor multiplet essentially is given by, so for the abelian case, just a self-dual BMN. So BMN has a field strength dB is equal to star dB. It has scalars and fermions, and they transform in the following representations, namely the 15,1, the 1,5, and the 4,4 on this group here. Okay, and that's basically a very simple theory, but we don't know much about what that theory is if we stack up more of these. And so then, the self-duality is one of the problems, but it's just a very complicated theory. We have very little tools to study it otherwise. So this was sort of getting this theory from branes. There's another way, of course, to get this, which is starting with some string theory. And so let's take type 2B string theory, and we put it on an orbifold of C2 by a group which is characterized by this ADE gauge group that we want so these are finite subgroups of SU2, and SU2 rotates C2. So for example, for the 8 n types, it will send Z1, Z2 in C2 just to a phase rotation, and Z2 to the inverse phase rotation, where omega is the nth root of unity. Okay, and the claim is this space, if I put type 2B string theory on the space, and I decouple gravity, I mean, it's a non-compact space, so gravity is decoupled, and just looking at what happens to this theory, it actually will give rise to this 62,0 theory. So how many people have an understanding? I need to ask this so I know at what level we're talking about these things, so I don't just talk over your heads, but actually to you. Who knows how to think about this C2 mod gamma ADE? What kind of space this is? Why this is? Where do you get these gauge bosons from? I'm sure Hiroshi knows too. Okay, so most people don't. Okay, do people know that this is sort of a version of a non-compact Calabi-Yau space? Yes? Yes? Team one. Oh, okay. Can I get an, okay, who doesn't know this? Let's ask it this way. Okay, so we will go through this now, and actually, just because you will see, this is not just an exercise to get you familiarized with this, but to actually sort of get some feeling for this geometry. And this will feature in almost all geometric engineering constructions. The C2 mod gamma is like a central object. So you need to really kind of get an idea of what that geometry is made of. So basically the main tool, and so this is just some algebraic geometric tools, but we'll go through it in terms of equations and see what's going on there, is that the key to understand this the geometry is to resolve it. So first of all, one thing that we will notice very quickly is that this has a singularity, and usually it's good to resolve singularities, so smooth the space. And we have to smooth this in a way such that it doesn't change the properties of the space too much. So we look at something which I will denote by C2 tilde gamma ADE over C2 mod gamma ADE, and this space here will be smooth, and this here is singular. Okay? And essentially what we'll see is that the smooth space has a lot of hidden structure, namely at the origin what we'll be doing is we'll be inserting additional spheres. And these are the spheres that we'll use in the reduction from type 2b to actually understand the reduced, where all these modes come from that then make up ADE type gauge group. Okay, so let's look at the case C2 mod gamma A. So we said this acts with the phase rotations. We have a Zn, this basic gamma A is Zn, and it acts by Z1, Z2 mapped to omega. Z1 omega inverse, Z2. And omega is e to the 2 pi I over n. Okay, so first thing is, these coordinates are not good coordinates. They are transforming under this. So it's useful to actually map this to a set of coordinates that are invariant under this action and write this geometry in terms of invariant coordinates. So the first step is invariant coordinates. So natural choice here is, let's say, x is equal to z to the z1 to the n, y equals to z2 to the n, and then let's define z as z1, z2. So these are invariant under this. So what we will do is we actually write down this line equation that these will satisfy, namely x times y is equal to z to the n. Right, so this basically describes the same space. And so x, y, and z I can now think of in terms of independent coordinates that satisfy this equation. So this describes the space as a hypersurface. There's an equation, algebraic equation, in some ambient space, surface in C3. Okay, so why is it singular? So it's singular. We take we call this here P, and then we take the derivatives, dx, dy, dz of P, and we put it at x equals to y equals to z equals to 0, they vanish. As long as n is larger than or equal to 2. So it's singular at that point. So what do we do when you have such a singularity? Well, in algebraic geometry, you say, well, let's eliminate that point from the space. So we actually blow up the space. So second step is blow up the singular point. And what we'll do is, and I'll explain some reasoning behind this in a second, we'll just say, well, let's put these coordinates now not to actually be independent coordinates, x, y, and z in C3, but actually projective coordinates. So the projective space is exactly engineered so then you allow its x and y and z to vary over C, but they can't all be 0 at the same time. Okay, so now we basically say these are projective coordinates. And so one way to realize this, we send x to x times some zeta, y to y times some zeta, and z to z times zeta. And then just postulate that they are projective in the sense that x, y, and z cannot vanish at the same time, or that x, y, z is proportional to x prime, y prime, z prime, if exists a lambda unequal to 0, such that is lambda x prime, y prime, z prime. Then our equation will become, let's just plug this in, this transformation here. The equation just becomes zeta x, zeta squared xy is equal to zeta to the n, z to the n, these new coordinates. Okay, so now the question is, all right, what have we done? So as we move in the space away from the point x, y is 0, that now has been removed, it's basically the same space as before, except at the point x equals to y equals to z equals to 0, that point has now been replaced by a projective space given by this coordinate zeta. So zeta basically corresponds to, so zeta equals to 0, corresponds to what's called an exceptional divisor, or exceptional new class in this resolution. So zeta equals to 0 is the So as you will notice, there's something happening here that now we can actually factor out zeta squared from this equation. And this will be important because I want to actually do a blow-up that retains the sort of properties of the space, namely that we started with something that was had a particular curvature, or a Ricci curvature, and so now we don't want to change this in this blow-up. So in fact, we can simplify the equation, so xy is equal to zeta to the n minus 2 times z, and now consider the space and ask, is this now smooth? And that'll depend on n. So if we now have n equals to, or greater or equal to 4, then in fact we need to repeat this process. So again, now it'll be singular and with x, y, and zeta equals to 0. Let's actually write it like this. And if we are at n equals to 3, in fact, we're sort of done, and in fact, the space that we get is already smooth. So if we have n equals to 3, then the equation is x equals to y equals to zeta z. And at zeta equals to 0, the equation then reduces to x times y equals to 0, which means either x equals to 0 or y equals to 0. So we said x, y, and z with projective coordinates. If I now look at the subspace x equals to 0, or the subspace y equals to 0, these actually correspond to subspaces in this projective space, and they're actually each of these two spheres. So in fact, these subspaces, they correspond to P1s, so projective one-dimensional subspaces inside this P2. Just plug it in, and then x equals to 0 just reduces it to the P1 given by y and z, and likewise for y. So what you actually get here is two spheres. And with a little bit more work, we can actually show that, in fact, the two spheres intersect. So in fact, the two spheres intersect. So actually the more accurate picture is the two P1s, they look like this. So this is the one that's x equals to 0, this is the y equals to 0, 1, inside zeta equals to 0. Okay, so this is actually the Dynkin diagram for A2. And if we had done this for the process for n larger than 4, we would have kept going, and in each of these steps you would have seen new spheres appear in this way. Right, so with every blow-up, there's a new projective space that we're inserting, and then looking at what type of geometries these have, they're actually given by spheres. And for the A type, so for AN, we will get sort of n such spheres, which each intersect in some Dynkin diagram for AN. So these are all P1s. And the intersection, so if I label these spheres P1I, then their intersection pattern in this geometry is given by the Cartan matrix. Of AN. And more generally, for the ADE types, in terms of the Cartan matrix of the ADE group. Okay, so more generally, for the ANs, we will get y squared is, the equation can always be brought in the following form, so I'll just write out the equations, and then you can maybe as an exercise just try to do these resolutions yourself. So for the D type, it's y squared plus x squared z plus, oops, this should be z. Z to the n minus 1. And then there are the three exceptional ones, E6, E7, and E8, which are given in terms of y squared is x cubed plus z to the 4 Okay, and in each one of these, repeating this process that I just sort of started off, so doing the blow-ups, always at the low side that are singular still, and you keep doing this until you reach the smooth geometry when the derivatives don't or vanish at some locus. So blow-ups yield collections of P1s, right? So topologically, there are two spheres intersecting in the corresponding ADE Dynkin diagram. And one other thing that's sort of a corollary of this is that actually the intersection matrix always minus the Cartan matrix. Pi squared is always minus 2. And that comes from the fact that you really should be thinking of these PIs as the simple roots of these Lie algebras. Okay, so how do we now get from all this 60 to 0 theory? Well, so this is sort of a relatively an old story, but let me just sort of explain this very briefly. So the 62,0 with G equals to ADE now comes from looking at this theory in the resolved geometry. So we have C2 mod gamma ADE. Right, so this is the resolved one. And now we can sort of reduce to be, in particular, the C4, which has the self-duality star DC4 in 10 dimensions. Reduced along these P1I yields, for example, the B. Oops. Okay. There it is. So the N of the tensor multiplet. At least in this way, you sort of see, morally speaking, where this would be coming from. And of course, the being away, so going to the, so this is basically on the tensor branch of this series. Where the volume of these P1s is greater than 0. And as we shrink them back to the singular point, at least the claim is that we're getting this strongly coupled conformal field theory. Okay. There's one other thing that I didn't really talk about here in too much. I just sort of, in the top row, I canceled the zeta squareds. This just makes sure that I'm not changing the canonical class. And this may be something that, if you've never seen this before, is maybe not something that's the most pressing matter on your mind. Okay, so this is a class of theories that is relatively well understood up to the subtleties that we know basically nothing about them, except that we know how to construct them in principle, right? So this is how, from string compactification or from M5 branes in M theory, we can get these theories. I was telling you earlier that for the 61,0 theories, recently there's been sort of a classification for these. So for 61,0, there's now a classification where we upgrade type 2b to F theory, and the C2 mod gamma ADE are replaced by some complex two-dimensional spaces B2, which are also, in fact, C2 mod some gamma, where now gamma is a subgroup of U2. Right? So here recall gamma ADE was a subgroup of SU2. And in fact, in addition to this, B2 is not just any kind of orbifold with some U2 action. There's also plus an elliptic vibration. So a T2 vibration, if you want, over B2, where the complex structure, the shape parameter, tau of this T2 is given by the axodilaton. Okay, so you should really think of this as some T2, this complex structure, fibered over now space, which will be a Calabi-Yau threefold, over a base B2, which is this orbifold. Yeah? And if this vibration is trivial, so it's T2 times the base, then you're back in the regime of the 2,0 series, right? Because you have sort of a product between this T2 and local K3. Right, so this is for the 1,0 case, and then you go back here for the trivial vibration. Where the Calabi-Yau 2 is now just C2 mod gamma AD. Okay? All right, and so just in the same way as what we've done for these P1s, when we did the resolution of these singularities that are ADE singularities, for the base B2 with these gammas, you can also do these blow-ups. And what you actually find is they have a very similar structure. So, in fact, these B2s, they're also, when you resolve these, they're morally speaking also a collection of P1s, but they now have some different, whatever, NKs. So these are also P1s, but with P1, the self-intersection of these is now minus Ni, and that doesn't have to be minus 2. Okay? But if there are negative, these intersection matrices are negative definite, and you have a consistent elliptic vibration, then you actually have putatively some conformal field theory as you go back to the origin, when you go back to the singular limit. So as you take the volume of these P1s to 0, and the intersection matrix, so the P1I dot P1J matrix is negative definite, and we have elliptic vibration, then this is actually a 6D SCFT with 1,0 supersymmetry. Okay, so one simple example is one that you might know. It's the E string, which is sort of the minimal object that you could write down, where you have a -1 self-intersection curve. Okay, so this is essentially just sort of, I know there are a lot of people here who work on conformal field theories, on ADS-TFT, and gravity, and if you are not sort of familiar with geometry and these kind of things, then at least this should give you some motivation why such things could be within your horizon to study. Okay, so given that this is essentially sort of a classification of such conformal field theories, you can ask, is it possible to push this further? Can I use such constructions to look at other dimensions, other supersymmetries, and look at field theories and their construction? So I want to just give an overview of what type of things are actually possible there, right? So geometric engineering for other dimensions and different numbers of supersymmetry. So I think the next thing where a lot of progress has been made is looking at 5-dimensional superconformal field theories, which you can obtain from M theory and Calabi-R threefolds. These are essentially the sort of M theory, F theory duals to the 6D ones. There are other ways of looking at sort of various ways of looking at 4-dimensional SCFTs, or just field theories, 4-dimensional, in fact, without saying superconformal, because at this point there is no way to sort of say specifically which ones of these are actually CFTs and which are not. There are lots of classic examples, so either constructions of F theory on Calabi-R 3 times T2, or K3 times K3. One thing that sort of always keeps showing up is that the spaces that one considers in all of these constructions, there are some type of Ricci-flat manifold, right? So you actually are looking at geometries that have particular properties, such as they're not just your generic orientable manifold, but they're actually Ricci-flat. So one question, if you're not thinking about these things day in, day out, is why are you looking at these type of manifold? When, in fact, do we preserve certain amount of supersymmetry? And for this, actually, it's perhaps useful to think, well, these are not actually the only options. There's sort of underlying theme why Calabi-Yau, etc., keep showing up in this context. So one question, which I'm sure you've sort of heard before, is when actually preserve supersymmetry in, say, a Minkowski space-time times compact space compactification. And for this, we of course have to look at the Killing spin equations. Which essentially say, without fluxes for the moment, and assuming Minkowski space, that you have to have some covariantly constant spinner on your space-time. So nabla, so epsilon. Yes, so there's maybe one little caveat that you need to take into account here. For F theory, this gets modified, namely nabla is then replaced with nabla minus IQ, where Q is now dependent on the variation of the isodilaton and is given in terms of 2 tau 2. I tau is equal to tau 1 plus I tau 2. Okay? And so, of course, in mathematics, spaces where you have such covariantly constant spinors are given in terms of a basic well-established list. This is this very famous Berger list of geometries. And essentially, the key to finding such covariantly constant spinor geometries is that you have to have a reduced holonomy. And why is this? Well, let's look at a very specific example. So just to get an idea why this is the case, so SO1, 10, say we're in 11 dimensions, and we want to compactify to 1, 3 times some compact manifold, which by basic algebra will be of dimension 7. So we would like to have supersymmetry in this. So our 32 component spinner in 11-dimensional supergravity will decompose into some spinner in 4 dimensions, tensor the 8 spinner under the SO8. And of course, generically, if you have this decomposition and SO7 just stays SO7, you will never find a covariantly constant spinner because, of course, it keeps transforming, right? It transforms as an 8 representation. And so SO7 is certainly, having a generic 7 manifold there is certainly not going to help you retain any supersymmetry. So in fact, if SO7 is further reduced to G2, which is a subgroup of the SO7, what happens is that the 8 spinner now actually decomposes into 1 plus 7. And this is now a totally different game because now we actually have a singlet and a chance that this will transform trivially on this reduced holonomy group G2. Right, so for we actually get, there's a singlet, so covariantly, so at least there's a singlet. And epsilon. And in fact, this will imply there's in fact a covariantly constant spinor. There's still a little sort of gap in here, but this is something that then follows from the existence of such singlet representations. Okay, so for most purposes that will appear in our sort of string theory kind of landscape, we will have the groups, which are the well-known SUN holonomy spaces, but there are others, and at least I want to sort of give you just a very brief overview of what type of holonomy one has and what kind of properties these spaces have, right? So if you, given the holonomy and the real dimension of the space, the Ricci is another important property of these spaces. Then if we have generic holonomy SON in n dimensions, this is just an orientable manifold. UN is Kähler, so there has to be complex manifold, and the Ricci, there's no constraint here, so this actually should be here. New statement about the Ricci, neither here, so these are Kähler manifolds. And then, of course, the ones that have SUN holonomy, they're again complex, the Ricci is 0, these are the Calabi-Yaos, the Calabi-N folds. There's SP2N, which has to be 4n dimensional, the Ricci is 0, these are the so-called hyperkähler manifolds. And one example is K3, which is a Calabi-Yau too, but in fact, they have 4n dimensional incarnations. And then there are the two exceptional cases. One we have encountered, which is G2, and the other one, which is spin 7, which is an 8 manifold. And again, the Ricci's are 0, and unlike the cases before, which are these ones here, which firmly live in the realm of algebraic geometry, and there are lots of tools to study them using these kind of tools that I've sort of sketched to you, like if you have a singularity, you can blow it up and you can deal with this in a concrete fashion. You can study these. Spin 7 and G2 holonomy manifolds are really genuinely differential geometric objects. Okay, so they are much more tricky to come by. Okay, so what actually do these geometries do for us in string theory? So maybe I will put it on the next page. So just to give you some idea of what type of compactifications we actually can get from this. So if R1, D minus 1, the number of supersymmetries. And then what is sort of the F theory or the M theory compactification to get these. So as I said, in 6 dimensions, there is the supersymmetry, which is 2, 0, and that was just type 2b. So that's T2 times C2 mod gamma ADE, or more generally a K3, which is a Calabi-Yau twofold. We said in M theory we can get these from M5 branes. 1, 0 is, as we also discussed, T2 fibrations over base manifolds B2 that are orbifolds C2 mod gamma U2. Now in 5 dimensions, we can have n equals 1 supersymmetry coming from Calabi-Yau threefolds. And then in 4 dimensions, which might be the most interesting, we have for n equals to 3, very recently, S folds in type 2b. For n equals to 2, these are the classic results, Calabi-Yau 3 times T2 or K3 times K3. In M theory, they're just obtained as Calabi-Yau 3 times S1 reductions. And then n equals to 1, we can get in F theory from Calabi-Yau fourfold reductions, or in M theory from G2. And finally, let me just finish this table and then I'll explain a few things about it. n equals to 3 can arise from SP4, so hyperkähler real 8-dimensional manifolds, n equals to 2 from Calabi-Yau 4, and then n equals to 1 from spin 7. Okay, and then of course you can also go to 2 dimensions, and then things become quite much more richer, because you have all kinds of P, Q supersymmetries. Okay, so in this table, there are some entries which we understand, how we have, where we have a criterion. When are these theories actually CFTs in the sense of, you put it on, you compact by F theory and M theory, and these are basically these examples here. Here we have a very good sense of, and then also as I explained for these here. So these guys are the ones where we know there's a geometric criterion for when something is an SCFT, or how to construct these. And there's also a classification, plus a classification. The case where there's a geometric criterion, but we don't have a full classification is the Calabi-Yau 3 case. So we have here the same sort of, at least a good understanding of what this means, but there is actually no, but not yet. And I think this is also true in the case of the S-folds, for n equals to 3. And then basically the cases where we have no understanding of these at all are specifically the ones with less supersymmetry. So in particular, 4-dimensional n equals to 1 is this case here, and also all the remaining cases, but I want to focus mostly on this case here. Right? So there's no sense in which we know when a compactification, say in F theory of a Calabi-Yau 4 fold, will give a 4-dimensional n equals 1 supersymmetric theory or not. That's conformal. I mean, it's always n equals 1 supersymmetric. I can write down a gauge theory, it has a property, but when actually it is conformal, that is sort of not a purely geometric criterion that we know. So some basic tools known how to construct, but there's no geometric characterization of when this is a CFT. And in the F theory setup, right, which was extremely powerful for the 60 case, the 4-dimensional n equals to 1 setup is much more tricky because, well, n equals 1 supersymmetry is much less, it's much more richer if you want to put it positively. In Calabi-Yau 4 folds, there's fluxes that one has to turn on and all kinds of non-perturbative effects which play into this, like D3 sometimes. So you can ask, perhaps one should also look into this other realm in G2, where at least from the understanding of how theories are constructed, everything is purely geometric. These are harder geometries to construct, but nevertheless, they're extremely, it's sort of a straight lace. You just have a geometric construction, and that determines what the effective filter is. So what I would like to do is, after giving you some broader overview of the types of things that one can do with geometric engineering, and I think the key one to take away is this case of this C2 mod gamma, which actually features in each one of these constructions here, is to actually now tell you what I plan to do in the next couple of hours. Namely, so the goal is to get some better understanding of these n equals to 1 theories are using M theory on G2 manifolds. The motivation is clear, I hope. So find basically basic geometric engineering dictionary. And give you an idea of what type of geometries these are. So overview of the G2 geometries, in particular compact ones, and the four-dimensional physics associated with them. Okay, so plan one is, well, some basics about G2. I assume most of you were not around in this field when that had its first sort of burst of activity, which was in the late 90s, early 2000s. So there's some sort of, for Calabi-Yau's, everyone has some understanding of the basics of them. For G2, I think that's less the case. The second thing I'd like to discuss is the gauge sector of M theory on G2. And this is a purely field theoretic analysis, and this sort of sets up the dictionary. So this is basically writing down the dictionary for G2 and for the n equals to 1. The third part is then giving you some idea of the compact G2 manifolds. And one reason why I'm talking about G2s for the rest of the time, sorry I didn't reveal this at the beginning because I thought maybe that would scare off more people than it would sort of attract. Because essentially, because there's some mathematics that actually has been, over the last years, sort of emerged, there's some progress in actually constructing these manifolds. So it is still not on the level of, writing down a huge database of these things, but now the database is sort of order 10 to the 3 or 4 that for the G2, which is much smaller than for Calabi-Yau's, but it gives you a good sense of what type of geometries one can construct there. And then finally, I'd like to discuss sort of M5 branes in G2 compactifications. Right, so one way of thinking of M5 branes is domain walls in four-dimensional n equals 1 theories, which preserve actually n equals to 1 supersymmetry. And of course, that has also recently seen quite a lot of activity, that kind of thing. Okay, so I should give you some references on G2. So I have done sort of an overview there. Some good reviews. There was initial activity on G2 manifolds. Mostly the papers that are sort of standing out there are by Witten, Atiyah, Maldacena, Acharya. There's a paper which has these authors, Atiyah, Maldacena, and Witten, which I think is a fantastic combination of people to write a paper on G2, so I think that's worthwhile looking at. There's a review by Acharya and Gukov for the very basic aspects of it. If you're interested in the math, there's a book by Joyce on special holonomy. That's very readable also for physicists. The new developments, I think, are more in the realms of these new compact geometric things. In the math side, this goes back to this Corti. Anyway, the math is here. this paper by Corti, Huskins, Nordstrom, Pacini, and I'll explain to you the construction of these manifolds. There's a sort of gauge theoretic description, Pante, Weinhold, and some paper that we've written last year, which just studies what is the gauge sector of a G2 compactification in M theory, and then lots of progress on these geometries that were developed. And then for M5 brains, I mean, there are lots of different papers, and I hope I will get to some of these aspects. Okay, so before we break, I would like to just sort of, yeah, actually maybe this is a good time to 2:30, 3:30. Okay, so I will start after the break with sort of the basics of M theory on G2 manifolds. And describe to you sort of what is G2, what is G2 holonomy, to sort of think about what is the effective theory of these, and then as a second part, probably the second half an hour, then tell you how, again, this sort of ADE singularity story will become important here as well to actually study gauge theories, or the gauge theoretic sector of these compactifications. Okay, so I think we break for 5 minutes, so at 3:35 we'll come back, and then for the rest of the lectures, I'll be focusing on these G2 manifolds.